All right, so let's get started on today's meeting. Today's final meeting for this semester. And today what we're going to do is we are going to do our final check-in and just review a couple of topics that students wanted one more look at. So this will be our final meeting where we, for the last time, take a look at some statistical strategies and procedures and try to fill in any final gaps that you wanted addressed. So the topics today came from the student survey that you completed, and we are going to try to check off as many of those as possible. And the two top topics that students indicated that they want one more look at ended up being t-tests and confidence intervals. So I combined those two because those were the actual second and third most requested topics separately. So we can take a look at both of them and we'll see why in just a moment. But then the number one requested topic was chi-square tests. So we will take another look at both of these ideas and topics today. So it's going to be an SPSS-heavy day today when we work through a few more do-it-with-me demos just to give you, in one case, one last look at how to run a particular t-test, and then take a look at a new way to calculate confidence intervals using SPSS, and then another way to calculate and do chi-square tests in SPSS, which might be a little bit easier for many of you, especially with the types of data that you might have access to. So all of that and more today when we take a look at t-tests and confidence intervals. And we're going to take a look at a study by Jauk et al., the relationship between intelligence and creativity, new support for the threshold hypothesis by means of empirical breakout detection. And then we're going to revisit chi-square tests with a look at a study by Pagnini et al., and it was called Unexpected Events and Prosocial Behavior, the Batman Effect. So let's get going on that first one there. So this is a study by Jauk et al., and it was a relationship between intelligence and creativity. And what they did is they did a study, and as part of this long-running debate in psychology about whether being more intelligent makes people more creative. So does more intelligence mean that you're going to be more creative, or is there a threshold where additional intelligence above that threshold really doesn't increase creativity? So up until that threshold, more intelligence would equal more creativity. But once you reach a certain amount of intelligence, adding more intelligence to a person will not increase their creativity. So there's been a longstanding debate between those two views. And the traditional idea of that threshold comes from a study by Guilford et al., who argued that intelligence and creativity are related only up to a point. And that point is usually found to be around an IQ of 120. And then once you reach an IQ of 120, beyond that threshold, intelligence stops predicting creativity. So the basic idea is that on average, somebody with an IQ of 120 will be more creative than somebody with an IQ of 100, but beyond 120, intelligence doesn't help with creativity. So if you're a genius with an IQ of 145, you are on average going to be no more creative than somebody with an IQ of 120. So that's the general consensus, but research was very mixed. A lot of the early research was mixed, and some supported a threshold. Others found a more linear relationship, and others found no relationship at all. So Jauk et al. Decided to tackle this problem. So what was it that they did to investigate the connection between intelligence and creativity? Well, they collected data from 297 adults, and what they did is they measured both intelligence and multiple forms of creativity. So they didn't just take a look at one type of creativity, they took a look at multiple forms of creativity. So the intelligence was assessed using an intelligence structure battery, and they were able to measure the IQ of each of the subjects. And then to measure creativity, they didn't just use one task, but they used a whole array of different creative measures. And what they looked at was the two that we're going to focus in on. The first one is divergent thinking. So divergent thinking is the creativity that you use when you are just kind of generating ideas that have not been utilized before. So, for example, in their study, they asked subjects to generate uses for everyday objects that are not what they're typically for. So, how many uses can you think of for a pencil? How many uses can you think of for a fork other than writing and eating with? And then they had self-reported creative activities and achievements. And this was creativity in the real world. So what have you actually created? What have you actually, problems that you've actually creatively solved in the real world? And what they found was that intelligence supports creativity up to a point. But after that point, other factors become more important. So they did find this threshold, evidence for this threshold theory of intelligence and its effects on creativity. But very interestingly, they found that the threshold differs depending upon the type of creativity that is being measured. So for a simple creative potential measured by their divergent thinking, so for example, how many uses can you come up with for a fork, that had a low threshold of an IQ of only about 86. But the threshold for real world creative accomplishments, where you were able to actually put your creativity into the real world in terms of real creative achievements, real creative solutions, that had a higher threshold of about 104. So those were the main take home results. However, one thing that they mentioned in their write up was that in order to obtain a heterogeneous and not solely academic sample, they recruited participants via a local newspaper as well as the university's mailing list. Inclusion criteria were an age between 18 and 55 years, German as a mother tongue, they did this in Austria, and the absence of neurological and or mental disorders. And they were able to find 297 respondents that fit that criteria. So what they were really trying to do is they were really trying to find a representative sample of the public. They didn't want to just solely rely on an academic sample, just solely rely on university students. They basically wanted to get a more representative, heterogeneous sample to stand in for the population as a whole. They wanted to be able to generalize beyond the university student. So they reported their descriptives in this table here, and we're just going to focus in on the IQ scores here. So importantly, they found that in their sample of 297 individuals, they measured a mean IQ of 107.21 with a standard deviation of 14.63. So the question now becomes, and the question that we're going to take a look at was, given this mean IQ and this standard deviation, was their sample actually from a population with a mean IQ equal to 100? So IQ scores are typically standardized to 100 in the population. So was their sample with an IQ of 107.21 and a standard deviation of 14.63, did it actually come from a population that has a mean IQ of 100? So to do that, we are now going to turn to our first Do It With Me demo. So if you haven't already, open up SPSS. And then also, if you haven't already, open up the T-Test and Confidence Interval Review SPSS demo Excel sheet that looks like this. If you're watching this on the video, the link is in the description. And this is hypothetical data that will mimic the findings that Jauk et al. Did. And I see an error right here. Let me just get rid of that right now. All right, so here we have the IQ scores that they measured for each participant. And as you can see, we have all 297 participants and their reported IQ scores. Here is the sample mean of 107.21. Here's the sample standard deviation of 14.63. And what we're asking ourselves is this sample from a population that has a mean IQ that is significantly different from, or that is different from a population with an IQ of 100? So do these people, do these individuals here, do they belong to the population that has an IQ of 100, or do they belong to a population that has an IQ different than 100? So we're going to go now to IBM statistics here. IBM SPSS. And we've had some issues recently with SPSS not taking in the decimal places that we wanted to, not transferring those decimal places from Excel into SPSS. So just in case, I don't think that's going to come up in any of the homework that you need to do, but just in case for your future uses of SPSS, so for example, in your advanced lab or in your future psychology work, one thing that you can do in order to safeguard that is you go down here to variable view. So we're going to click on that. And we're just going to start by putting in the name of our variable before we paste it in. So we're going to put in the name of our variable here, our dependent variable, and we're going to call that IQ scores. And that is 8 or less. So we're going to be all right. And then for the type here, it defaults to numeric. So once you put in your scores name here, if you just click on the type column here, it'll bring up numeric automatically. And then it brings up this window here. And we want to go over here to where it says decimal places. And we want to change that from the default of 2 up to 7. So 7 is the maximum that you're allowed to use for this particular configuration. So we're going to put in, rather than the default of 2, we're going to put in a default of 7, and we're going to hit OK. And now in this data view, if we go back to the data view here, you can see that we have the variable, it's already named, it's already ready to receive numeric data. And importantly, it's ready to receive numeric data with 7 or more, with up to 7 decimal places. So now we can go back to our Excel sheet. And then the last part of this is to make sure that the decimals that you want are visible in your Excel sheet. So again, this is going to come up when you're doing your own research. So we want to make sure that the decimals that we want, for example, the 7 decimal places, are visible in the Excel sheet. So if they're not already, I put it already formatted in this Excel sheet. But if they're not, you want to go up to these 2 buttons over here. And if you just hover over them, it'll let you know what they do. So this button over here is decreased decimal. This button over here is increased decimal. And you can just play around with these when your cells are highlighted, and it will change the number of decimals displayed for as many as you want or as few as you want. So if you need whole numbers, you can do that. If you need, as we do, 7 decimal places, you can do that as well. So we got 1, 2, 3, 4, 5, 6, 7. So however many you need and you want in SPSS, make sure that those are displayed. And then we've already selected our data, so now we can copy it. We go Control C. We're going to allow that to happen. And then we go back to SPSS. We click on row 1, column 1. And just to be on the safe side, we're going to go up here and we are going to try to paste. Let's see if it'll, yeah, it did that old thing. All right, so you'll notice that because we put this as numeric, it did not allow us to put in that value of V. So again, we're going to go back here now that SPSS is ready to go, and we make sure that we've copied our data. We can go here, we can go Control V, or use the paste option in the file drop-down menu. And then finally, we have the SPSS, the Excel data transferred into SPSS with all the decimal places. You can see them there. And that's going to give us a level of accuracy that we want. That's going to give us a level of accuracy that allows us to replicate what other people have done in part of this learning environment. And when you're doing your own research, you always, always, always want to mitigate and minimize any round off errors that you can. So as many decimal places as you can carry, as many as the software will allow you to, it's a good idea to carry that, because decimal places that are rounded off have a tendency to accumulate error and get us further and further from the truth. So use the machines. For what they're good for, one of the things that they excel at is remembering long strings of numbers. So use that to your advantage to get as accurate as you possibly can. Okay, so those are our scores. That's our sample. We want to know, does this sample belong to a population that has a mean IQ of 100? That's the null hypothesis. They belong to the population that is a mean IQ of 100. The null hypothesis is that they do not belong to that population. So we are going to run a one sample t-test because we have one sample of data and we're comparing it to a known population mean or a hypothesized population mean. And in this case, it's the known population mean of 100 because IQ tests are standardized that way. So we go here to analyze. We go back to compare means and proportions. We go back to the one sample t-test here. And then we have IQ scores, and that is the test variable that goes in here. And then in terms of options, remember that this is where you can set your confidence interval percentage. And we're going to leave this at 95 for the time being, but that is the default. So we're going to hit continue. And then importantly, down here for test value, that is where you put your null hypothesis mean. That is where you put the population mean from the null hypothesis. So we want to test, does our sample come from a population that has a mean IQ of 100? So in that test value, we got to make very, very sure that we put in a value of 100. So we double check the test value. Again, that is your null hypothesis mean. So test value equals 100. That looks good. Everything is good to go. We click OK. And we get this particular output here. All right, so take a moment, compare your output to the output that I have on the screen there. Does anybody's not look like that? Looks good. All right. So let's start interpreting this, and we'll take a look at what this t-test analysis has told us now. So here's the output, and let's zoom in on the important tables here. So first off, always check your descriptives. SPSS very nicely labels this descriptive. So if we had more than one dependent variable, then it would have a table and we could see which variable was on which row. We only have the one row, but still it's nice. It says IQ scores to jog our memory, make it a little bit easier cognitively. And then we want to check the number of scores. We want to check the mean. We want to check the standard deviation. So SPSS lets us know you have 297 in this sample, mean of 107.21, standard deviation of 14.63. All of that matches what we have in our Excel sheet. So we know that we have copied and pasted correctly, we have entered it correctly, and we've entered the data at a level of detail and precision that we wanted to achieve. So nothing's been rounded, everything matches, we're good to go on to the next step. And that next step is to take a look at this one sample t-test table here. And this only has the one row, nicely labeled with IQ scores. So this is the t-statistic and the degrees of freedom. So this t-statistic is what SPSS calculates that lets us know how far does our sample deviate from what we would expect a sample to look like if the null hypothesis was true. And that t-statistic of 8.49 is really not very meaningful to our human minds because it is totally based upon things like the degrees of freedom in this one sample t-test. But importantly, just know that the larger that t-statistic is, the further and further away your sample is from the null hypothesis. The further and further away our sample is from belonging to a population that has a mean IQ of 100. But the one that you want to look at in this case is this column right here. So it's labeled significant, specifically two-sided probability, two-sided p-value. And what that basically says is that to get a sample with the mean and standard deviation that we found in this study, to get a sample like that, the likelihood is less than 1 in 1,000. So you have less than 1 in 1,000 chance of finding a sample this extreme if it came from a population that has a mean of 100. So if it's highly unlikely that this sample came from a population with a mean of 100, that means it's highly likely that it came from a sample without a mean of 100, with a different mean, some different IQ average. So the last thing I want to mention about this interpretation is that the reason we're choosing two-sided probability values is that we had no good reason to predict that the IQ scores that we collected in our sample before we took a look at them, we had no good reason to predict that they were going to be higher than 100 or lower than 100. So we need to honestly test for both of those in our t-test here to say, hey, we don't know if it's going to be larger than 100 or smaller than 100. We don't know if it's going to the right tail or if it's going to the left tail of the distribution. We don't know if it's going to the right side of the distribution or the left side of the distribution. So the only fair test is to do a two-sided t-test and use that probability or that p-value. The mistake you don't want to make is seeing that your sample goes in one direction and then testing whether it goes in that one direction. Because that is being dishonest, that is loading the deck and loading the dice in favor of finding what you want to find, and that's not what we're here to do. We're here to find the truth. So if you predicted before you looked at the data that IQ score should be higher, then we would do a one-sided t-test and use that extra power that we can get from doing a one-sided t-test. As soon as you look at your sample and see if it's bigger or smaller, if you haven't already made a prediction, you got to go two-sided. You have to go to that honest test of, we're not testing for a specific direction, we're just testing, are they different? In this case, the probability that it belongs to that null hypothesis IQ 100 population is less than 1 in 1,000. So the probability that it belongs to a population with a different mean IQ is very, very high. And in this case, we can conclude that this sample actually has a higher IQ. All right, so that would be the basic idea of the t-test. Once you find that the IQ of your sample is actually higher, once you find that your sample comes from a population with a higher IQ than 100, you might ask yourself, well, how much higher? How much more IQ does this population have on average? And for that, we need to go to a confidence interval. So now we're going to try to estimate how much more intelligence, how much more IQ, how much higher is the IQ of the population that we got our sample from. And it's important to realize that we are looking for how much higher is the IQ of the population this sample came from, because in this case, SPSS is calculating that 95% confidence interval, but very importantly, note that it is the confidence interval of the difference. So what does that mean, confidence interval of the difference? What that means is that it is comparing the sample's IQ scores, and it's asking how much different is it from the null hypothesis IQ scores. So it's taking what we know about the sample and estimating how much different is that mean difference there from our test value. So notice that our sample mean IQ is 107.21. The mean difference, that value right there, is 7.21. That is telling us that our sample comes from a population with a mean difference, a higher IQ, and it's higher by 7.21 points. And it's higher than 100 by 7.21 points. So again, this is giving you a confidence interval, not of what their actual IQ is, it's giving you a confidence interval of the difference between their IQ and a population with a mean IQ of 100. So that mean difference right there, that is your point estimate. That is the center of your confidence interval. That is your best guess. If somebody wanted you to give them one number, and just one number, that would let them know what is your best estimate for how much higher is the IQ of the population that we got these subjects from, you would say, well, my best guess, my single estimate is 7.21 IQ points higher. Now, on the other hand, oftentimes you don't want to rely on just a point estimate because those tend to be inaccurate. Because if it's 7.21, then you've successfully estimated the mean difference. If it's even 7.22, you've missed. You've got it incorrect. So that precision comes at a cost, and that cost is zero confidence. So you can have a highly precise estimate, 7.21, but that comes along with zero confidence. So if you need to make decisions where you need to have a certain level of confidence in order to make those decisions, then we go to a confidence interval. So SPSS very nicely has calculated that confidence interval of the difference. And we know with 95% confidence that the actual difference between our sample's population and the typical population has a lower boundary of 5.54, and it has an upper boundary of 8.88. So in other words, we can say that that 95% confidence interval of the difference between our sample's population and the typical population is an IQ score of 5.54 minimum up to 8.88 maximum. 5.54 is your lower bound, 8.88 is your upper bound. You don't know where within that boundary the actual difference between your sample's population and the typical population is, but you are 95% confident that that interval there contains the truth. You are 95% confident that the actual real difference is somewhere between 5.54 and 8.88. And then finally, if you want to put this into a different format, oftentimes in non-APA publications, you will see a confidence interval reported as 7.21 plus or minus 1.67. And the 1.67 is simply your mean difference minus your lower bound. It's simply the distance from the center of the interval to one of the bounds. And the easiest way to get that is just take your mean difference value and subtract from it your lower bound, and you will get that plus and minus value, and that is your 95% confidence interval. All right. So that's one way to calculate a confidence interval using SPSS. One of the issues with this and using this method, using the one sample t-test to calculate these confidence intervals, is that oftentimes people are not interested in the difference. Oftentimes people are actually interested in the complete value, not the difference, but the actual value. So for example, I might ask these researchers, well, what is your estimate of the IQ level for the population that your sample came from? What is your estimate for the mean IQ for the population that you got this sample from? Because clearly it's not from the typical population with an mean IQ of 100. So what is your estimate for the IQ of this mystery population? And in that case, they wouldn't want the mean difference because there's no way that this population has an IQ of 7.21. That is way lower than I believe you can even survive having an IQ that low. So we don't want the difference often. Sometimes we want the absolute amount. Sometimes we want the total amount. And sometimes calculating that total amount can actually get kind of complicated. So what we're going to do right now is we're going to see how to use SPSS to calculate that total amount, not when you want a one sample t-test done, but when you just have a sample and you just want to estimate that population parameter. So let's say that we just had, where'd you go? Let's say that instead of this output here, and we'll close that down. Let's say that we just had these IQ scores and we weren't comparing them to anything, and we just wanted to bring to somebody's attention what the average population IQ is for the sample that we got this from. How would we calculate that actual value? Well, surprisingly, it's pretty much exactly the same thing that we've done with just one little tweak. And you can do this for any sample that you are trying to calculate a confidence interval for. So if you have a sample that is just standalone, you just collected a sample, you're not doing a t-test, you're not doing any sort of research on it, other than you want to estimate the population parameter that it came from, you can use this technique. If you're doing a one sample t-test and you want to calculate the confidence interval of the sample that you're using, you can use this technique. If you're doing a independent samples t-test, if you're doing a paired samples t-test, if you're running ANOVAs and you want to calculate confidence intervals for your individual samples, you can use this technique. So it's a way to calculate general confidence intervals. So it is very versatile and it's a little bit hidden. And the way that you do it is this. We've been doing it all along. We just need to do one tweak. So first off, make sure that your sample data is in SPSS, properly formatted, properly entered. And then we're going to go to Analyze, and we're going to go back to Compare Means and Proportions, and we're going to go back to One Sample T-Test. And in the options here, make sure that the confidence interval is set to what you want. So in this case, we're going to keep it at 95, and then we'll show a variation in just a moment. So we have it at 95, so we hit Continue. And then this is the important part here. You go to your test value, and you enter in 0. And by entering in 0, now SPSS is going to continue to calculate that confidence interval of the difference. But now the difference is your population's mean IQ minus 0, which equals your population mean IQ. So we're going to make sure that that test value is entered in at 0. And then we're going to hit OK. And we get this output here. And we're going to go through this output right now. So again, double check yours to make sure that it matches up with this output here, that we've done it correctly. And if it has, let's go and take a look at how to interpret this. All right, so here we have the output. We'll zoom in a little bit. As always, I would be remiss not to say, check your one sample statistics, but I will just quickly go through this to just show you that this is exactly the same data that we've already used. So we reused the data. We haven't pasted and copied anything, copied and pasted anything new in. So let's go down to the one sample t-test here. And again, it's for IQ scores. And we're going to skip the t-statistic. We're going to skip the degrees of freedom because those are meaningless right now. And if you take a look at them just real quickly, that t-statistic is 126. That's a massive t-statistic because this is a one sample t-test that is asking, is our sample different from a population with 0 IQ? And evidently, it is very different than a population with 0 IQ. But that's not a research question that we're interested in. What we're interested in is the 95% confidence interval. And that 95% confidence interval is still the confidence interval of the difference. But now take a look at that mean difference. That mean difference is 107.21. And that is the mean of our sample's IQ. So that mean difference now has changed. And the reason is because our test value is 0. So we're comparing our samples population. How different is it from 0? And that is basically an estimate of what the actual population parameter is based on our sample. So that's the mean difference right there. And very nicely, SPSS has calculated that lower bound, and SPSS has calculated that upper bound. So now we have a 95% confidence interval of the population mean IQ that our sample came from. And we have a lower bound of 105.54, upper bound of 108.88, and put it in the other format. We have the mean difference, 107.21 plus or minus mean difference minus lower equals 1.67. So that's how we do a 95% confidence interval. And then if we needed other confidence intervals, we would just go back to SPSS. We can clear that out. Just go back to Analyze, Descriptive Statistics, Compare Means and Proportions, One Sample t-test. We go back to Options, And if we want, for example, a 99% confidence interval, we enter that into this options, one sample t-test options. We click continue. Make sure that your test value continues to be 0 when you're calculating these confidence intervals. We hit OK. We get this output right here. And if we take a look at the output, zoom in on that, same old one sample descriptives has not changed. In our one sample t-test, again, not interested in the actual t-statistic or the degrees of freedom because we're not doing a significance test here. We're just looking out at the 99% confidence interval of the difference. But that mean difference of 107.21 is compared to a test value of 0. So it's the actual absolute difference, is the actual estimate of the population parameter. Notice that the mean difference or the center of your confidence interval hasn't changed. So that center is always your best guess. It's just how wide around that center that is dependent upon the size of the confidence interval. And now because our confidence level has increased from 95 to 99, our lower bound has gone lower to capture some more confidence, and our upper bound has gone higher to capture some more confidence. So our interval overall is wider than it was for the 95% confidence interval. So now we have for our 99% confidence interval a lower bound of 105.01, an upper bound of 109.41, or 107.21 average plus or minus 2.2 in terms of IQ score. All right, so again, that is a very straightforward way to calculate confidence intervals for any sample, and you can use this regardless of what test you're actually doing. So if you're doing a one sample t-test, feel free to use this. If you're doing a independent samples t-test, paired samples t-test, ANOVA, if you're not doing a significance test at all, but you need to generate a confidence interval, you can use this technique and this strategy to let SPSS calculate that confidence interval so you can estimate a population parameter based on your sample. All right, any questions on that? Okay. Item number 1, off the checklist. So t-tests and confidence intervals, we're done with that. And now we're gonna move to chi-square tests. And I'm gonna show you a new strategy to do the chi-square test, which will be more in line with the information that you will often have access to. So to illustrate that, we are going to go to this very recent study. I actually learned about this study a week after I did chi-squares in this course, and I was very, very sad. It didn't come out before, so I could include it as an example. But I was very, very pleased that, well, I'm not pleased that students were struggling with chi-square tests, but things have lined up in a nice little way. So this is a study by Pagnini et al. It's called the Unexpected Events and Prosocial Behavior, the Batman Effect. So in this study, researchers rode the Milan subway system, and they staged a simple scenario. So in a control condition, a woman, actually an experimenter, boarded the train and appeared to be pregnant. So she was dressed in a way that made her appear to be pregnant. She wore a prosthetic belly, and she would stand in the aisle and wait to see whether seated passengers would offer her a seat, and an observer stood nearby and recorded what happened. So that was a control condition. A woman who appeared to be pregnant would come in and would be standing in a metropolitan subway system and just waited to see if a passenger would offer her a seat. That's a control condition. In the experimental condition, the same pregnant woman boarded the train, but another experimenter, and this is the key here, dressed as Batman, entered through a different door about 3 meters away. So there was no interaction between Batman and the woman. Batman didn't speak, Batman didn't gesture or even look at her. Batman simply existed in that environment that the passengers found themselves in. And then the question that they asked was very simple. It was simply, would the presence of Batman make people more likely to help? So these researchers predicted that unexpected events might momentarily, and this is an unexpected event, typically you don't see people dressed as Batman, but they might momentarily disrupt any automatic behavior, pull people into the present moment, and then heighten their awareness of other individuals' needs by cueing this idea of a heroic identity. And in this case, this heroic identity would call for them or push them to offer that pregnant commuter a seat, to give up their seat for that pregnant individual. So each of these rides, they lasted about 2 to 4 minutes. They did 138 of these, half of them with Batman in the car, half of them without Batman in the car. And they just recorded whether anyone stood up and gave the pregnant woman their seat. So I would be remiss if I did not say that this is the research that the world deserves and the one that it needs right now. This is one of the coolest studies I've ever come across. So what did they find? So this is a table with the observational report. And what we have here is we have the condition, and we have the experimental condition, Batman was in the car. We have the control condition, Batman was not in the car. And down here we have the total observations, and there were 68 observations in the Batman experimental condition, 70 observations in the control condition. And then importantly for us, we have the scores for prosocial behavior. So how many individuals exhibited prosocial behavior? That is, how many people gave up their seats in these particular conditions? Well, in the experimental condition, 41 individuals got up and offered their seat to the pregnant woman. And in the control condition, 29 individuals offered up their seat to the pregnant woman. So that's the reported data. We're going to run a chi-squared test on this to see if people were more likely to give up their seat when Batman was present in the car than when Batman was not there. And then the last thing that we need for this information, or the last thing that we need to run this chi-squared analysis, is the number of individuals that did not exhibit prosocial behavior. We need that for our table. So that's pretty easily figured out. How many no prosocial behavior instances did we have? We can simply take the total number of observations in each condition and subtract the number of prosocial behaviors. So there were 68 individuals in the experimental condition, 41 of them offered up their seat, and that means that 27 individuals did not offer up their seat. And there were 70 individuals in the control condition, 29 offered up their seat, and that means that 41 individuals did not offer up their seat. So now we're going to see if we can do a chi-squared analysis for association on this data here to take a look at, do we have evidence that the presence of somebody dressed up as Batman actually increased prosocial behavior in this instance. So for this, we're going to go down to SPSS, and just one last time, and I apologize if this is loud, but given the issues that we've been experiencing with SPSS these days, this is one of the scenes that's been in the back of my mind every time I open up SPSS. And as a Batman fan, I just couldn't let it pass. So here it goes. I apologize if it's loud. This is what I keep thinking of when I open up SPSS.
Now you want to get nuts? Come on, let's get nuts.
All right, let's get nuts. Let's do this. All right, so back to SPSS. We're done with the one sample t-test, so we can close that. We don't need to keep that. We don't need the IQ scores anymore, so we can click on that and we can just delete it, just to kind of clean up our work environment, just to kind of make sure that we don't have any residual stuff to make our interpretation even more difficult than it actually is. Okay, so this is going to be our little step-by-step guide for how to do this analysis if you don't have the scores for every single participant. So if you recall in previous versions of this, we would have row upon row of scores here where it would say something like, well, subject number 1 was in the no Batman condition and did not give up their seat. Subject number 2, Batman condition, did not give up their seat. Subject number 3, no Batman condition, did give up their seat. So we would have the individual scores for each particular subject. Don't need to go back to Michael Keaton. So we have the scores for each individual subject. But sometimes you don't have that. In fact, oftentimes you don't have that. And if you don't want to go through the extra step of creating that in Excel from the descriptive data reported in these reports, there is another way to do it. I'm torn on whether it actually saves you work or is just additional work. But importantly, there's another way to do it. I wanted to show you that. So we are going to, whoops, Michael Keaton will not be denied. We're going to take a look at that and see how to set that up. So it's very different in terms of setup than what we've typically been doing. And what it starts with is it starts with a trip down here to variable view. So we're going to get out of data view. We're going to click on variable view. And what we're going to do is we are going to set up 3 variables here. And the first variable here is going to be called condition. So we type in condition, and then for the type here, we're going to click on this. And we kind of missed it, we're not really getting a nice little hover thing, but it's these 3 dots here. We're going to click on that, and we're going to change this to string. So what this is telling them is that we are going to change this to a word. This is going to be language data. This is going to be word data. It's not numbers. They're going to be strings. They're going to be words. So then we hit OK, and we got ourselves our first condition set up. The next variable that we're going to have here is going to be prosocial. There we go. And then you can see that it automatically changes this to numeric. So we're going to click on that. And this is also going to be string over here. And just to be on the safe side, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We are going to change this to 11. Just to make sure that we have enough for the variables that or for the values that we're going to enter in. And then the last variable that we have here is going to be called count. And that one actually is numeric, so we don't have to change anything. It's the default, but if we click here, we can see that it is now numeric. It's going to, SPSS is going to expect a number in that column. So we have on the first variable condition, that's a string. On the second variable prosocial, that's also a string. On the third variable count, that's numeric. So if we go back to data view, we can see here, and I'll just drag these out a little bit. We got condition, we got prosocial, and we got count. And those little circles there means that condition and prosocial are strings. That little ruler measuring thing means that count is a numeric value. Okay, what we're going to do now is we're going to set up 4 rows of data. And we're going to start off with the conditions here. And what we need is we need to enter in every single combination of Batman and control conditions and seat offered and no seat offered outcomes. So for the first row here, we're going to type in Batman. And then we can go over to the prosocial condition here, and we're going to type in seat offered. And then for the count here, we're going to enter in how many people in the Batman condition offered their seat. And if you take a look at the original data, and I don't want to swing there right now because I don't have it properly displayed, but if you take a look at the original data, that is 41 individuals. 41 individuals out of the 68 in the Batman condition gave up their seat. So that's the first row there. Notice that row, unlike what we've always done, contains 41 individuals. So this is a very different way of using SPSS, but it's a way that you can do the chi-square test using not the actual raw data, but using summary data like this. All right, so that's our first row. Next row, Batman. This one is going to be people in the no seat condition, people that did not offer their seat. And again, if we check with the descriptives reported in the study, we can calculate that this was 27 individuals. So now we've completed the Batman conditions. We've covered everybody that offered a seat and everybody that did not offer their seat. Now we need to do the same thing for the control condition. So we go to row 3 and we enter in control. And we're going to start off with the seat offered condition. And we are going to type in how many people offered their seat in the control condition. And from the study, we find that that is 29 individuals. And then finally on that 4th row, the last of the control condition, this is the no seat condition. And we are going to type in 41. And again, should have mentioned this earlier. Notice that seat offered, no seat, they don't have any spaces. SPSS sometimes gets very finicky about spaces. So we are going to keep that as it is right now. All right, so this is the way that we set it up. And again, notice that we have not the raw data, but the actual summary data here. But we're still going to have SPSS able to enter that. All right, so you can tell how often I do this because I have my steps written out. So now let us go down to step 3. So the next thing that we need to do is we need to tell SPSS that count is the actual frequency. And we're going to do this by weighting the cases by. So we're going to go up here to data. So up here on the file selections, we go to data, and we're going to go down to weight cases. And that's all the way at the bottom. So we go to data, travel all the way down here to the bottom to weight cases. And then you're going to indicate what variable you want to weight the cases by. And basically what that is telling you, or telling SPSS, is which one of my columns there actually contains the frequencies. Which one of my columns actually has the numbers that indicate how many people are in each case, how many people are in each combination. So in this case, we only have count, and we want to not select the do not weight cases by, but we want to select here the weight cases by. And you'll notice that as soon as you do that, it highlights or activates this little arrow here. So again, it just is asking you, where are the frequencies? Which one of these variables has the frequencies that you want these cases analyzed by? And in this case, it's count. So we just move that into frequency variable. We have count, and once we do that, we hit OK. So once you do this, if you do it successfully, you're going to be able to go down and take a look down here in this little corner, and it will say weight on. And that is what lets you know that, okay, you are now weighing the cases against the count variable here. So you're good to go. It's all ready to go. So now we can go on to step 4, and we can actually run the chi-square test. So to run the chi-square test now is exactly the same steps as we previously used to run a chi-square test, in this case for association. So we go to analyze, we go down to descriptive statistics, and we choose crosstabs. And again, chi-square is one of those tests that is hidden in 2 separate spaces, depending upon whether you're doing goodness of fit or associations. So in this case, we're doing association. So we need to remember and understand that that is in analyze descriptive statistics and crosstabs. So here we have the crosstabs dialog box. And for the rows and columns, that is simply asking you which one of these condition and prosocial variables is going to be the row and which one is going to be the column. Typically, well, not typically, it does not matter which one you choose as the rows and which ones you choose as the columns. SPSS will come to the same conclusion every single time. However, typically, what you believe to be the cause of the behavior is going to be in your rows. What you believe to be the outcome of the behavior is going to be in the columns. So we are testing whether the presence of Batman is causing prosocial behavior. So we are going to take condition here, and we're going to put that in rows. And we are testing whether Batman caused seats to be offered or no seats to be offered. So for that, we're going to take prosocial and we're going to put that into columns. And again, it does not matter for the final analysis, but this is just a convention that is oftentimes used. So we put those into the rows and columns. We leave count here. We're not going to use count. And then we're going to go over here now that we have condition and prosocial in the places they need to be. We go to statistics, and we're going to ask for the chi-square, because we're doing the chi-square test for association. And we're also going to calculate phi and Kramer's B for effect sizes, because oftentimes when you're interpreting your chi-square, you want to have those effect sizes. When you learn more about chi-squared analyses and frequency analyses, you'll learn about what all these other ones are doing. But for the time being, in this intro to statistics, we are just going to choose chi-square and phi and Kramer's B. So we hit continue. And then importantly, in cells, this time we are going to choose observed, and we're going to choose expected. You don't need to choose expected when you're typically doing an analysis, but for illustration purposes here, I want to make sure that we have expected chosen. And then that's all that we're going to choose, and we are going to hit continue. And now that we have everything ready to go, we are going to hit OK. And as you can see, SPSS has run us a chi-squared analysis, even though we did not have the raw data, even though we did not have the individual rows corresponding to individual suspects. So this is a very different way of using SPSS. But importantly, whoops, let's go back to that output. Importantly, it has now given us that chi-squared analysis that we were looking for. All right, so now that we have the chi-squared analysis done, let's go back and interpret it. All right, so there's the analysis that we just did. Let's zoom in on that real quick. So in this case, we're going to skip that top table there because the descriptives that we need are actually in this condition times prosocial cross tabulation. This is basically your 2x2 table of Batman and control versus no seat and seat offered. So as you can see, we have the conditions listed here. So we have the Batman condition when Batman was present. We have the control condition when Batman was not present. And then we have the counts here. So that first row, that count is telling us that 27 individuals did not give up their seat when Batman was present, and 41 individuals did give up their seat when Batman was present. We can check with our data. We know that that's the correct number, so we feel confident in that. And then in the control condition, we have 41 individuals that did not give up their seat and 29 individuals that did give up their seat. And again, those are the correct frequencies. Those are the correct numbers. So those are the actual counts. That's the actual data. That is what the researchers went out there and found. What SPSS has also calculated for us in this case is the expected counts. And the expected count for the Batman condition is that 33.5 people would not offer up their seat, and 34.5 people would offer up their seat. And the expected count in the control condition is that 34.5 people would not offer up their seat, and 35.5 people would offer up their seat. Now, what are these expected counts? The expected counts is your null hypothesis in numerical form. The expected counts are what you would expect, hence the name, if the null hypothesis was true. If Batman's presence did not make a difference in how many people gave up their seats, then we would expect that out of those 68 individuals that were in the subway car when Batman was there, 33.5% of them, 33.5 of them, not percent, 33.5 of them would not give up their seat. 34.5 of them would give up their seat. And then when the control condition was present and Batman was not in the car, out of those 70 people, we would expect that 34.5 people would not give up their seat. 35.5 would give up their seat. And those expected counts You can calculate them by hand. Basically, what they're doing is they're saying, well, what is the actual kind of proportion that we have in the no seat condition and the seat offered condition? And then it maintains that proportion for the expected count in the control condition and the expected count in the Batman condition. That's kind of the behind the scenes look at what a expected count is actually doing. Importantly for us though, not only does SPSS calculate that, but that is your null hypothesis. So in a world where Batman makes no difference to people's prosocial behavior, those are the counts that we would expect. If we ran this experiment over and over and over and over again, those would be the average counts that we would find in this experiment. These are the counts that we actually found in this experiment. So what SPSS does and what a chi-squared analysis does is it basically says, all right, I'm going to take these actual counts that you found and I'm going to compare how extreme are they if we expected these values to occur. So these are the values that we actually got. These are the values that we expected. This is what we found. This is what we should have found if the null hypothesis was true. So how unlikely is it to get numbers like this? 27 no seats, 41 seat offered, 41 no seat, 29 seat offered in the control condition. How likely is it to get numbers this out of whack, this weird, if in reality, the world that we live in is not affected by the presence of Batman? If that is actually the world that we live in. So again, is this a weird sample that belongs to this null hypothesis world? What the chi-squared test does is it figures out how weird is this sample? How likely is it to get a sample this extreme if this is the actual truth of the world that we live in? So SPSS calculated that out for us. So here we have our chi-squared test table. Importantly for the chi-squared test, especially in this intro to statistics, we're only looking at that top row with that Pearson chi-squared analysis. The chi-squared statistic that was calculated was 4.912. And again, this is a measure of how extreme was this sample. How unlikely was this sample to occur? How different was this sample from the null hypothesis sample? And a chi-squared distribution has a degree of freedom of 1, so SPSS will calculate all that out for you. But importantly for us, and importantly for the interpretation, we have this asymptotic significance two-sided. That is your p-value. So that is the p-value for your chi-square test. I don't know why they don't have the letter p there. Sometimes SPSS is very friendly, sometimes not friendly at all. This time not being friendly at all. But basically the p-value for this test is 0.027. And what that means is that you have a 2.7% chance of getting results this weird if this is the actual truth of the matter. If Batman does not have an effect on people's prosocial behavior, you will get values that look like this or more extreme only 2.7% of the time. So there's a 2.7% chance that we live in a world where the presence of Batman does not have an effect on people's prosocial behavior. That is extremely unlikely. What that means is that it makes it highly likely that we don't live in this world, but we actually do live in a world where Batman's presence does make an effect on behavior. So again, the probability that we live in a world where Batman's presence does not affect our prosocial behavior is 2.7%. So it is very likely that we actually do belong to a world where Batman's presence does affect social behavior. And this chi-squared test has shown us that that is significant. So we reject the null hypothesis that we live in a world where Batman's presence makes no effect. And we accept the research hypothesis that Batman's presence actually increases prosocial behavior. All right, any questions on that analysis, that setup? All right. So that is basically it for what I wanted to cover in this course. So this is a bit of a momentous occasion here. So I'm going to leave you with another Batman quote. And Batman said, "The world only makes sense if you force it to." And that, depending upon your own views, you might take that as true, you might take it as false. But whether you believe it or not, whether the world only makes sense if you force it to, you now have the tools to make sense of the world. And you now have tools to actually force the world to reveal its secrets, to reveal the truth that is hidden behind what we observe, and to get minimize and remove any of the biases that we as humans bring to our interpretation of data, any of our limitations that we as humans bring to understanding the numbers. We actually now have systems and procedures where we can take a look at studies that were done, take a look at data that we have collected, remove our own biases from the analysis of that data, and actually force this world and psychology to reveal its truth to us so that we can try to make sense of the world. So I hope this course has helped you in your understanding of statistics. Just as a final mention, I will one more time just say that this is an introduction to statistics course, and we have introduced you to statistics and covered, I would say, about 90% of the tests that psychologists use most often when they're doing their data and when they're doing an analysis. What that means is that we've left about 10% still on the table that we have not covered. So what I am just giving you an invitation is that when you are doing your advanced lab or your senior seminar or any of your capstone courses, and you need to do statistical analyses, highly recommend review some of the lectures that you've seen in this course. Statistics is one of those courses, and this is unlike any course that I've ever taken, and I've talked to many students who back me up on this assertion. Statistics is a course where once you finish your statistics course, your mind will do a buffer dump of just about everything that you have learned this semester. And when you revisit it, you will wonder if you've ever taken a statistics course. I am saying that because number one, that's true. So a semester from now, maybe a year from now, when you're getting down to do your advanced lab, you're going to sit down and you're going to say, all right, I'm going to do some stats. I'm going to do some SPSS. And you're going to open up SPSS. You're going to open up, your raw data, and you're going to think to yourself, did I actually take an introduction to statistics course, or was that just a fever dream that I had? Because I can't remember how to do any of this. That's the bad news. The good news is that it comes back almost instantly once you get back into it. So that is my public service announcement. Don't panic. Don't worry. Go back to your textbook. Go back to some of these videos. Just rewatch it. And I guarantee you, in about an hour or two, you'll be sitting there going, oh, of course. That's what you're supposed to do. That's what that is for. That's why this makes sense. It's all coming back to me. So you will have that experience. Just be aware of it. Just be prepared for it. It's coming. Don't sweat it. It happens to everybody. You'll be fine. The other thing that I want to mention is that we did cover 90% of what you're probably going to encounter. That means we got 10% that you are not or have not been introduced to. If something comes up, especially if you're doing your advanced lab, and you come to a situation where you say to yourself, all right, I've designed this experiment, and it's not a one sample t-test. It's not an independent samples t-test. It's not a paired t-test. It's not a chi-square test for goodness of fit. It's not a chi-square test for association. It's not a one-way ANOVA. What am I supposed to do? In that case, I invite you, contact me, come by my office, and I will take you through the steps that you need that go beyond this introduction to statistics course, because that is exactly where I want to get you, where you are comfortable with the tests that we've introduced today. But I also want to support you in your future statistics endeavors. And the one that's coming up is your advanced lab. And it has happened to student after student after student, where they design great experiments that just go beyond what we've covered in this class. and then they feel as if maybe they didn't learn enough in statistics, or maybe they've taken a personal failure, that they've forgotten everything. You haven't. There is that small little section that we haven't covered. So again, this is my open invitation that if that's your situation, don't knock on my door because I'm barely ever here. Send me an email. I will do my best to respond to it. We can set up a Zoom meeting, and I'm more than happy to go through the statistical designs to answer those questions. Other than that, is there any final questions or anything that anybody would like to ask? Okay, then for the last time, that is all that I wanted to cover for today. So thank you so much for joining me on this journey. I hope it's been successful, and I wish you great luck and great success in all your future psychology and statistical endeavors.